Good morning, everybody. My name is Oliver Mannerholt, and I'm going to talk about stainless steel and passivation for stainless steel today. A few words about my person. I'm originally from Germany. I studied brewing science. I moved to the States in 2011, so about 13, 14 years ago. And I'm now working for C. Loeffler as the technical director for the brewing division and also the regional manager for the West Coast. I'm also doing a lot of presentations, so welcome to my presentation. So stainless steel is a very nice tool, especially now in the food industry, but all the other areas like to use stainless steel. Here are two extreme examples, I would say. One is the famous Gateway Arch in St. Louis, which has a 304 stainless steel series. For those of you who have been there, you know, it's a really nice, cool experience, even going up inside. Another extreme is one of the latest fighter jets the US Army has, the F-35. It's an extremely high strength and light series 600. So just to give you an example what stainless steel can mean. What is actually steel? What is metal? So let's go back a little bit in history. Quite a large portion of our Earth crust is metals, and it's one of the earliest material actually used in prehistoric times. You know, in the old days, we called about ages, so Copper Age, Bronze Age, and so on. So that's when these different metals were discovered and used until the 18th century, when we got basically into the Industrial Revolution, and we were able actually to make more out of all the different metals in the crust. Mostly they are all in a not a purity, they are combined with other elements, and so they're called ores. The only one which is kind of exceptional is gold, which shows up as pure metal. So if it's not if it's pure, it's and there's no other contamination or other materials in it, it's called a pure metal. And if it's mixed with other metals, iron, copper, zinc, etc., then we talk about alloys. So this is the two major differentiation. So we have, for example, brass or stainless steel. These are alloys because we're going to add a certain other metal or other material to the copper, to the steel, to provide different features, different specifications. Sorry. Oops. Okay. We talk about ferrous and non-ferrous metals. So ferrous metal is, for example, iron and carbon. Non-ferrous is mostly pure metal, zinc or bronze. And then ferrous metal can be alloy metals which contain, next to the iron as a base, other compounds. And the same applies for non-ferrous metal. So they also contain other elements, but not into iron. Some examples for classification. So on the left side, we have iron, low carbon steel, medium and high carbon steel, cast iron. Then, of course, the stainless steel we will talk about more, tool steels and everything else. Whereas non-ferrous, you know, famous things like aluminum, copper, brass, bronze, zinc, and so on. So that's a big challenge sometimes in the brewing industry. You know, all the equipment is stainless steel, but here and there you find non-ferrous metals like a copper pipe or aluminum cable tray close by. That makes it a little bit harder in the application of either passivation or cleaning in general. So how do we get to the iron? You know, so it's found as an oxide in the earth crust. So we have three ores primarily. It's a magnetite, hematite, and tectonite. And how is it extracted? It's basically done by a blast furnace. So first we're going to wash the ores, crush and mix it with limestone and coke, so to improve the actual process in the blast furnace. Then this mixture is fed on top on the into the furnace, and then depending on the mixture, the coke, which is basically part of the coal, it's a high carbon content, that helps basically to convert the iron oxide to pure iron. Limestone is also added to basically remove some of the impurities to increase the purity of the metal. Then at the end, we will have basically two separate items. The one is the slag, which is basically all the liquid waste, which is floating on top of the molten iron, which is tapped off separately. I'm sure you've seen already some documentaries where, you know, people poke it and then you get this really heavy stuff, the slag on the one side and the liquid iron on the other side of this. Even with, you know, really good blast furnaces, the purity is only 90 to 95%. Then we can actually, with further pure oxygen furnace and so on, or electric arc furnace. That's what helps you to even remove more of the impurities and to increase the purity significantly. So the different items which are fed to the blast furnace is basically fed to from top in different layers. The ore is the iron, the coke is basically from the coal, and created by heating it in the oven. And then the limestone acts as a fluxing slag, like as a kind of a filter to remove impurities. We have pretty high temperatures. We talk about at least 1100 degrees to go in there, and then it gets even higher, almost up to 3000 to get the molten iron in the bottom. And I will show you a little picture here of one of these blast furnaces. You can see in the top, the conveyor feeding the different items, and you have layers in there. And then from below, you can see the heavy blast of the heat going in there. And this basically liquefies everything, and then it collects in the bottom. And you can see on the right side, you will have a little bit above, you have the floating layer of impurities with the slag, which will be then drawn off. And a little bit further down on the left side, you can basically see the tab for the actual molten iron, which is then removed and then furtherly processed. So when we have the iron, the pure iron is a very soft and ductile, and this has pretty practical use. But when you add carbon to it, you start creating an alloy. And then we talk about carbon steel. And depending on the carbon amount you put in there, you can actually vary the hardness of the steel. Typical ranges are from like only 1.1% up to 4%. Type of steels is, when we talk about the regular ones, the low carbon steel, the medium carbon steel, the high carbon steel, and cast iron. And when you talk about the alloy steels, then we talk about stainless steel or high-speed steels, which are used for certain tools where we have a very high speed or very high impact, where the steel needs to fulfill certain specifications. Just to give an idea what materials, typical items we daily use are made of. So when you talk about low carbon steel, you can see there are pins, nails, screws. So they have a very, very low carbon content, from 0.05, maybe up to 0.3%. They're tough, ductile, mealable. They're poor to corrosion. So it's, quite often you see that the nail is rusting. But it's a very general purpose item, and it's often used also in construction. Now we go up a little bit further. So we increase the carbon content up to 0.3 to 0.5%. So it has more strength and more hardness, but then it's less ductile and mealable. So now we are talking about, larger structural steel beams, rails, garden tools, everything where the impact on the metal is higher, and we need to create a more resistance so the steel doesn't break, the steel doesn't bend. And then last but not least, we go to high carbon steel or tool steels. The carbon content can go up to 1.5%. It's very hard, so the ductility and the mealability is lower. So it's quite often a hand tool, if it's a chisel, if it's a punch, a saw blade, a hammer. So all these different tools where we have a very strong hardness to fulfill the goal, whatever the tool is used, needs a very high carbon steel. Cast iron, that's when the carbon content really goes up to 4%. It's very hard and brittle, but it's very strong under compression. So as you can see here, we have, for example, a motor block, which is mostly out of carbon steel. Nowadays, quite often also aluminum. And although the carbon steel can be poured at lower temperatures, makes it really easy to work with. But although other alloys or other parts where we need to have, good strength made from the cast iron. They are different cast irons, white, gray, ductile, mealable. They are either, hard and brittle, good for wear resistance, rolling and crushing equipment, for example. Gray one is comprehensive tensile strength, machinability, vibration damping. So it's a machine base, a crankshaft, a furnace door, engine blocks. So you have a lot of different type of contents of carbon providing a different strength, a different specification, and the application for the different ones makes it so ideal. So stainless steel is a very good iron-based alloy, which has approximately 12% chromium. And this is used to prevent this from rust, from corrosion, and especially in an unpolluted atmosphere. As we all know, stainless steel, also some people call it, it's non-rusting steel, which is only partially true, but I will talk about this a little bit later. So we have all kinds of different elements we can add to the stainless steel, although to get different type of stainless steels. The main alloy elements is chromium, nickel, and carbon. So chromium is basically 12 to 14%. It's basically forming this kind of center cubic form in a ferrite element, and it's very high in for the concentration to get a lot, the boundaries. So in other words, the impurities on the outside, the intergranular corrosion is reduced by that. So that's very important because we want to make sure that if you have a corrosive atmosphere, that not immediately elements in the stainless steel will start corroding. Nickel is another element which can be added. It's authenticity to the stainless steel. It's very ductile, it's very well to form it, and it's tough as well. Weldability, which is very important because we want to get a good welding seam. We all talk about hygienic welding seam. So it's also adding a lot of strength to high temperatures during the welding, for example, and it's also helping to reduce the corrosion capability, so increase the aqueous corrosion resistance when it's basically underwater. Carbon is again to help the authentic strongness or strength, and it could be replaced by nickel, but carbon is 30 times more effective than nickel. Mostly it's a very low carbon concentration. As you can see, it's like only 0.8 to and 0.03%. That's all important during the welding process. Other elements which can be added is manganese or molybdenum. They basically is either an alternative. You want to substitute a nickel. Concentrations for manganese can vary between 2 and 3%. And molybdenum is a very good pitting corrosion-resistant material, added between 2 and 4%. It also helps to decrease the chromium concentration, but increases the nickel concentration. But this is very important, especially if you want to have a very aggressive corrosive environment, and that significantly helps for corrosion. There are other ones. I don't want to go too deep into that because that gets too extreme for these tungsten, nitrogen, titanium, and so on, for very specific applications, which are way past our field we are talking about. So now looking at the table of typical stainless steels, if you look the top right, you can 304, which is nowadays probably the most common stainless steel used to create all the equipment in the brewing industry, if it's the piping, if it's the brew house equipment, if it's the fermenters, and so on. If you go back in the past, probably quite often you saw more 316s, which is a higher grade. It's a little bit better than 304, but of course, all the more expensive. And the difference is not that dramatically. I would say if you have a good pre-maintenance schedule for passivation, cleaning properly, I think you can have the same life expectancy out of a 304 stainless steel equipment versus a 316 stainless steel equipment. And then if you go further down, these are getting very extreme, either if you have high chloride levels or high temperatures. But the 316, 304 specifically for our typical temperature range, corrosiveness from cleaning and so on in our food and beverage industry. Stainless steel, when it's newly made, it's cleaned of an oil and grease. I have seen this already. When you get a new piece of equipment, there's always kind of an oily film on it. Most important it is that we remove this oil or grease. First of all, we don't want to have any contamination of our products, but also when you want to passivate your stainless steel surface, this oil is basically a perfect protector, so the acid will never touch the stainless steel and will not passivate it properly. The passive layer will start automatically developing, as soon as there's oxygen in the air and it has contact with it, but it's very, uncontrolled. So we have here and there a little bit, and of course, depending on when the oxygen is used up, like inside of a pipe or inside of a tank, then the passivation slows down. So the idea is that passive means it's unreactive. So you create a layer between the stainless steel and the other side, wherever your product is. And this layer basically protects the actual stainless steel from direct contact with the product. So what we do is we take about 4 chromium elements, add 3 oxygen elements, and create 2 chromium oxide elements. And this is the layer. It's very thin. It's only a few molecules thick, and it's invisible. I always kind of describe it. It's a very fine glass layer, which basically separates the stainless steel from the product side. It is kind of fragile. So if you do something mechanically, it crushes, it breaks, and that means you have to redo a passivation. But that helps to basically prevent the iron, which is part of the stainless steel, for oxidation, corrosion, and so on. So surface damage, once it's installed and everything, you have to create the passive layer at the end, before, when everything is done with attachments, welding, so all the mechanical or even high temperatures impact on the equipment is passed. Then we need to make sure that we properly clean the surface and then properly passivate the surface. So like I said before, the natural reaction immediately starts, but you want to have it a very defined way of passivating the layer. So we need to do certain chemical applications to create that. Oops. So this passivation helps to, protect the stainless steel from corrosion. The layer itself is called passivation, or the formation of the layer is called passivation. But as soon as you have a mechanical tool, abrasion, some people, unfortunately, you'll still use like a Scotch pad on cleaning something, that immediately destroys the passive layer. And if the tool is harder than stainless steel, it will also scratch this stainless steel surface. So that will actually open up the doors for really good corrosion. So whenever you use something to the piece of equipment, make sure before the next use, perform a nice passivation procedure. There are all kinds of different specifications out there. We like to recommend the ASTM A967. But there are so many more out there, and more are developed. Of course, it depends in which field are you, and in from the industry, but also what the environment allows you to do. Nitric acid, sodium dichromate, citric acid, citric paste, temperature, time, etc. These are all the different specifications or parameters you can use to create a passive layer. So when was it kind of discovered? So Harry Braley, it's an English metal specialist, was actually working on a rifle barrel, and accidentally, like most discoveries, happened by coincidence, not really on a purpose, when he added chromium to low carbon steel, and he found out that this is a stain-resistant stainless steel metal. So that was what they say. That's when the stainless steel was born. It is indeed not really stain-proof, so it still can be discolored. It still can be rusting. It still can be damaged. But then with all the different additives to create the different versions of alloys, which we have discussed before, you can improve the different protective systems. Chemical passivation, basically it's a 2-step procedure. First, we need to make sure that the surface is absolutely free and clean. In other words, you want to remove the oil if it's a new piece of equipment. So you need some kind of a solvent-based cleaner to get this completely away. And then we still have some free iron molecules sitting on the surface. And if you see that as a little island or a little spot, that is actually the danger, because that's where you can start having corrosion. So once that iron molecule corrodes, it can basically transfer then the corrosion into the stainless steel. And once it reached a certain depth inside of the stainless steel, you have a problem, and then it's really hard to get this fixed. So what we can do is we can use certain acids to remove them, to dissolve them, to basically remove any negative impact on the surface of the stainless steel before you actually start the passivation, because the problem is the passive layer can actually immobilize this little particle, and then it has like a little passage, so you can actually then easily have from a corrosive liquid through this iron molecule through the passivation layer access directly to the stainless steel, and this is then at the end your negative pitting spot. So we have about 12% chromium in our stainless steel, and as soon as the chromium gets in contact with oxygen, it will come to what we see, the chromium oxide. And what we try to do during the passivation to force as much chromium to get a nice even layer with a certain thickness throughout the whole equipment, to get like this nice liner inside of a tank or inside of a pipe, to ensure that we have a good separation between the stainless and the product. So like I said, to get a thick and uniform layer, we want to make sure everything is free of any contaminants. As soon as you apply any mechanical action, abrasion, etc., your passive layer is destroyed. So what you can do, you can basically restore this whole thing by applying a new kind of passivation process. But still, I would first really clean everything and make sure that all the other particles, dirt, whatever is on there is removed. Problem is, so far, there's no consensus on the dynamics of passivation, how quickly it happens, when does it stop, and so on. So it's kind of a guessing step. We have a lot of experience nowadays with when you follow certain procedures, you have kind of a guaranteed one, but the actual dynamic, the clear picture of how quickly and why it's growing so far has not been fully discovered. Before you do the passage, like I said, a cleaning is very important. Just the grease of your skin when after cleaning your tank, you removed all the oil, you removed all the other impurities, and you just touch it with your hand, the surface. This little bit grease from your skin is already enough to protect the stainless steel, and then when you run a passivation procedure and rinse everything out later on, you can actually see your handprint. So this is a very important thing, that the surface of the stainless needs to be absolutely free, accessible to oxidation, either from a chemical or from the oxygen in the air. Like I said, it basically is a natural occurring process, but due to the fact that the dynamics is very significantly, we try to create a standardized environment, so we have a very defined growth of the passive layer. So on the other hand, it's basically that the iron in the stainless steel immediately also reacts with the air or with water, so that also then basically creates rust. So we have like a little competition between the chromium and the iron with oxygen, but when you do it properly, you actually have a good chance to overcome potential rust with a nice protective layer. The passive layer is due to help you from corrosion of your stainless steel, but also to improve your shelf life or life expectancy of your equipment. And if you redo it every year and make sure that everything you do to your equipment is properly done, you can have a very, very long time with all the stainless steel equipments. Basically, there are kind of three categories how to create this passive layer. Nitric acid is a very good one. It's called a little bit of an old version of it. It's the very strong oxidizer, so it really forces the chromium to create the chromium oxide layer. A new version is the citric passivation. Citric is much better for the environment. It's much better for the health of the working people, so it's nowadays a preferred method. Keep in mind the citric acid is not really oxidizing, so it's cleaning the surface, but then you rely on the fact that the oxidation takes place with the ambient oxygen of your air. Nitric acid is with or without sodium dichromate, different temperatures, different concentrations. Sodium dichromate is something which you can use outside of the food and beverage. In our industry, it's totally forbidden because it's a very toxic element. So this is absolutely not allowed. So we rely basically on pure nitric acid. And, many reactions, as you know, when you increase the temperature by 10 C, about 18 F, the chemical reaction doubles in speed. So you can actually shorten the time when you have a higher temperature, or you can shorten the time when you have a higher concentration. So all these different factors play a role. But I would say a standard procedure, which then because you don't want to get too high in concentration. It's a very dangerous chemical. All the high temperatures, I would not go too high. As soon as you start creating fumes will basically condensate on other metals and immediately corrode these other metals. So it's a balance between temperature, concentration, and time. And when you don't exceed the temperature and the concentration, but increase a little bit the time, you're more on the safe side. Citric acid, similar, the same applies to that. But like I said, you use in a much lower concentration, you more clean it, and then you basically rely on the oxygen. I was talking a while ago to the German Federal Material Research Center, and 800 to 1,000 barrel tank needs, after citric acid passivation, about 2 weeks to get fully passivated. And you have to ensure that the air is always saturated with about 21% of our oxygen. So you have to attach a blower to the tank and make sure that there's always fresh air going in, because the oxygen will then decline as soon as it reacts with the chromium, and you have to make sure it comes back in a proper concentration. But like I said, it's a very long lasting and sometimes not really a well-defined formation of layer. A complete different one is electropolishing. Some people like to use it because it also helps significantly to smoothen the surface, but it's a very elaborate and very expensive procedure. But I would say the electropolishing is only for very special points in the brewing industry. If you have like a cone of a fermenter and you want to make sure that the yeast, when you basically take out the yeast, slides easily down, that might be a part where your electropolishing would be beneficial. But if you have a beautifully built stainless steel and a nice passivation, you shouldn't have any issues. Citric acid, although very interesting, it was actually developed in our industry. It was developed by Coors Brewing. And although it helps to reduce the kind of weird metallic flavor which can happen when you do the regular passivation with nitric acid, I always recommend, when you have finished all the passivation, when you finish the final CIP after the passivation, to rinse the tank with old beer, which you can sacrifice, to remove the metallic flavor. Beer has a different pH, beer has carbon dioxide in it, so it will pick up the remaining flavor, which has not metallic flavor, which has not been removed with the regular passivation, caustic acid and so on. So that is another step I would recommend to avoid any metallic flavor for the first couple batches of beer in a freshly passivated tank. Mentioned before that citric acid has two strong advantages. The EPA loves it because it's a much less environmentally harmful chemical, although OSHA likes it because the concentration is much lower and the aggressiveness and the hazard is much lower. So from these two perspectives, the citric acid is a big favor, whereas I'm always still a favor of the nitric acid, because the speed and the reliability of a good formation is higher than with a citric acid. So when you start doing it, the most common is still nitric acid. You basically apply it in a strong concentration, about 20%. It's one of the strongest oxidizers in the acid world, so it really creates pretty quickly the chromium oxide layer, and it happens immediately. It's like, as soon as the nitric acid touches the surface and it sees a chromium element, it will create the chromium oxide. And then if you basically vary it, like I said before, with concentration and temperatures, you can kind of manipulate the formation of the layer. Times 20 to 2 hours. Like I said, when you want to do it quickly, higher temperatures, higher concentrations. If you want to do it longer, you can actually reduce. 70 C or 160 F is already pretty high in temperature. I would be very cautious because that's when you create fumes that, creates a lot of danger to the environment and especially to the people working there. Concentration can be, between 20 and 50% by volume, which is quite a bit. We normally say 20% nitric acid concentration is enough for 20 minutes at elevated temperature, so maybe 120. As soon as you see fumes, I would go a little bit down and maybe just increase the time to this. One more thing you need to should keep in mind is, the nitric acid is very aggressive, very corrosive, so it's pretty harsh on your gaskets. I always recommend when you have all your equipment and everything is freshly passivated from day one after it was installed, then you start operating, and after a year when you start repassivating, that you have a special set of gaskets, so which are not so, if they get a little bit damaged, if they got cracks and crevices, we don't really care. But if you then use those in the production and you have a biological thing, then we do care about cracks and crevices. So I would say have a dedicated set of gaskets when doing the passivation. And the passivation layer doesn't really change much its concentration, so you can use the same batch for the first tank, second tank, third tank. What I still would recommend between the switches from one to the other tank, ideally, if you have like an empty tote or drum, depending on the volume, store it in there. Don't let it sit on your gaskets inside of a fermenter, for example. And also check the concentration, just so that you have an idea how much you lost. So you can actually spike it up a little bit, going back to your target concentration. And then you can basically move on to all. And in a perfect world, when you did all the pre-cleaning, everything perfectly, your nitric acid solution shouldn't change any in color. Otherwise, you have something dissolved, which then is in the acid. Although you should ensure that there's no other particles inside. That means either you dissolved something or the cleaning has not been fully done. Citric acid time varies, like I said before, depending on concentration, temperature. It's more like cleaning the surface, so you need only ambient or moderate temperature. Concentration can vary between 4 and 10%, so it's a very light acid. As mentioned before, it's safe, it's biodegradable, and so on. So although for the people on the job, it's less harmful. There are a lot of positive things to why using citric acid. Just keep in mind, it is not 100% reliable like nitric acid, and it takes some time. So there's some, light and shadow to this. Dichromat, as mentioned before, it's a very strong oxidizer. It can be added to the nitric acid, but it's a total no-go in the brewing and food industry because it's a very toxic chemical. Passivation. We get often asked, how can we test? How can we see how the passive layer is actually formed? And because the passive layer is clear, it's so thin that you don't see anything. So the problem is how to test it. And there are a few tests out there. Some are really extremely elaborate or complicated, but they have some side effects which we don't like because they are so-called destructive tests. So to actually, like the ESCA, is the electron spectroscopy for chemical analysis. And when you say it's a destructive test, it's basically you need to cut out a sheet from your equipment to perfectly test it, and then you can actually see if how thick the stainless steel layer is and how well it was built up. But like I said, then you have a hole in your tank. This is definitely not a go. The Auger electron spectroscopy is very similar, and so that we don't want this applied. So there is no real test where you can hold something on it and see, okay, it's 0.3 nanometers thick or whatever. Because if you just look how thin this is, it's like a hair or even less than a hair. It's a very, very fine layer. It's very good with liquids, but mechanical action, it's very weak to this. So what you can do is there are other tests out. They basically tell you if there's any impurities. It's only spot tests, so you don't get the whole picture of the tank, but you can, it's like little coloring agents, and they react with a different color if it touches like an iron molecule, which is basically immobilized inside of the passive layer. But this is a tool just to get an idea how well you actually did the pre-cleaning. But it's only like a few spots. So from the statistical reason, it's not very good in information, because you don't want to do like hundreds of these tests to get a nice big tank, checked. But coming back to the passivation, we talked about kind of a summary. The freeing everything, all the free molecules have to be removed. We want to do a nice chromium oxide layer, which is completely closed. There's no something built or immobilized in this chromium oxide layer. And I would say nitric acid versus citric acid, it's up to everybody who wants to do it. It's, there are pros and cons for each. I'm more on the nitric acid because if you do it properly, there are two big advantages versus the citric acid. You can actually, the safety aspect is big, but if you do it properly, with your proper PPE and so on, and you don't heat it up too much, it's like with any other corrosive liquid, you have to take all the precautions and don't be nervous. Just, know your stuff you're doing, and then it's okay. The other thing is, I'm sure you can do the same with the citric acid, is you can collect it, recollect it, and utilize it again, either for the next passivation, or even if you have already a pre-diluted nitric acid solution, and you can use it as a CIP chemical later on. Just make sure everything is properly labeled, tested for the concentration, so that everybody passing by a tote or drum with this particular acid knows what's in there. And if you have a fully automated CIP system, which based on conductivity, it will automatically draw. Of course, it will draw a little bit more because we have already a dilution factor in there. It's like, depending how you phrase it, citric acid gains more and more, but there are still vendors out who'd like to promote the nitric acid. I would say everything can be dangerous, everything can be safe, no matter what. From my experience and what we have seen so far with problems or not problems, the nitric acid seems to be a little bit more reliable, especially if you don't have much time. Give you an idea. So you have the chromium, the little red dots inside of your stainless steel. You have your oxygen, the oxidizers outside. And as soon as they touch, they create a very thin layer. And you can see it's like 1 to 10 molecules thick. That's not a lot. And we talk about 1 to 5 nanometers. So it's a very, very fine layer. And it's actually, compared to our hair, even sometimes thinner. But this is the typical procedure of the passivation. Different tests showed, how quickly it grows and how thick it can grow, depending on the different methods. So the top graph, where you have after 240 hours, the thickest layer, that was basically a 60-minute nitric acid. Then if you use like an oxidizer, like hydrogen peroxide, it's already thinner. And if you don't have any treatment, and you just rely on the pure oxygen, that's where you get about half the thickness, like from the nitric acid. And keep in mind, you need to make sure that your oxygen content is always 21%. As soon as the tank is, the oxygen content inside of the tank will decrease, of course, the reaction of the chromium oxide will slow down and basically inhibit a further growth. When to passivate, this is also a good question which we get often asked. There is no standard rule outside. So first of all, I would always say, whenever you get new piece of equipment, you remove all the oil, clean it thoroughly, and do your first passivation. Then whenever something has been done to the equipment, either it's a damage because something dropped, a metal tool dropped in the tank, or you had added a pipe, there was some welding done, so you have a pretty high heat impact. That definitely is a point for passivation. And then because the passive layer, although in a regular application, will start declining over a certain period of time, so a repassivating on a yearly basis is what we always recommend. But depends. And then, of course, it all is depending what is on the other side. So what kind of chemicals, what kind of aggressiveness, what kind of corrosiveness of liquids are sitting or touching the passive layer. So there are a lot of differences which also might increase the repassivation frequency. Aggressive foods, like when you have a high chloride level, things like that, or very acidic, like tomatoes or tomato juice and salsa, though tomato is one of the most acidic produce. So that basically calls for a higher passivation procedure. Although when you have water with a high chloride level, that although calls for a higher frequency of passivation. And then if you go into the pharmaceutical industry, then there are more rules out there, and they say it's 4 times per year. Although the high purity of water is also a big problem, because if you have RO water, please don't store it in a stainless steel tank. Rather have a plastic tank, because the hunger of pure water, leaching out elements from the stainless steel is very high, and it can actually significantly damage your equipment. Although the pharmaceutical company has a very strict rule on the roughness of the surface. Of course, the more often you run equipment through, liquid through, the stainless steel surface will get coarse and rougher. And there are certain limits. So then quite often pharmaceutical companies just replace the equipment with freshly new stainless steel. The passivation actually has a little bit of a smoothing effect. So if you have a little bit of a roughness in your stainless steel, the passivation can kind of even it out a little bit, not only to a certain degree. Another thing is when, for example, iron deposits are, when there's a little bit rust, and then they say, okay, it's time to repassivate it. So there, like I said before, there are test kits out to see if there's any free iron sitting on the surface as a potential corrosion point. And if you find more and more of those, then I definitely would start passivating. That leads me to a very neglected piece of equipment quite often in the brewing industry is the HLT, the hot liquor tank. It doesn't have the same attention like a mashing tun, a loader tun, a fermenter, and so on. So quite often people take it for granted, and it always provides hot water and the brewing liquor. And depending how the water was treated before, if it was dechlorinated or it still has chlorine, if it's harder or softer. So there are different ways of, basically adding damage to your HLT. So if you have hard water, it will precipitate out, create a nice thick scale inside of your tank, which needs to be removed. And how often you have to do this, it depends on your hardness of the water. Some breweries have to do it every 2-3 weeks, run a little acid cycle to remove all the scale. Others, when they have very soft water, they can wait 6 months or even more. So that is very important. Besides, the scale is another protective layer from a damaging chloride to the stainless steel. So between the stainless steel wall and the scale, you can have some chloride molecules sitting, and nothing is happening to them because the scale protects them, and they can start really now pitting your equipment. We have customers, they basically opened after 2.5 years the first time the HLT, found a lot of scale, cleaned it out, and then had to call the manufacturer and were told that basically this tank is not fixable and a new tank has to be put in because the corrosion reached a degree where fixing is not possible anymore. So like I said, a very aggressive area is the HLT because varying parameters, heat, scale, calcium, magnesium, chloride levels keep an eye on it and descale it on a regular basis. And then once a year, do a passivation on it. And your HLT will be very happy. Thank you so much. And now, please, any questions?